11.7 Strategy for Testing Series. We now have several ways of testing a series for convergence or divergence. The problem is to decide which test to use on which series. In this respect, testing series is similar to integrating functions. Again, there are no hard and fast rules about which test to apply to a given series, but you may find the following advice of some use. It is not wise to apply a list of the tests in a specific order until one finally works. That would be a waste of time and effort. Instead, as with integration, the main strategy is to classify the series according to its form. Number 1. If the series is of the form the sum of 1 over n to the power p, it is a p-series, which we know to be convergent if p is greater than 1 and divergent if p is less than or equal to 1. Number 2. If the series has the form the sum from a times r to the power n minus 1, or the sum from the sum of a times r to the power n, it is a geometric series which converges if the absolute value of r is greater than, it converges if the absolute value of r is less than 1 and diverges if the absolute value of r is greater than or equal to 1. Some preliminary algebraic manipulation may be required to bring the series into this form. Number 3. If the series has a form that is similar to a p-series or a geometric series, then one of the comparison tests should be considered. In particular, if a sub n is a rational function or an algebraic function of n involving roots of polynomials, then the series should be compared with a p-series. Notice that most of the series in exercises 11.4 have this form. The value of p should be chosen as in section 11.4 by keeping only the highest powers of n in the numerator and denominator. The comparison tests apply only to series with positive terms, but if the sum of a sub n has some negative terms, then we can apply the comparison test to the sum of the absolute value of a sub n and test for absolute convergence. Number 4. If you can see at a glance that the limit as n approaches infinity of a sub n does not equal to 0, then a test for divergence should be used. Number 5. If the series is of the form the sum of open negative 1 close to the power n minus 1 times b sub n, or the sum of open negative 1 close to the power n times b sub n, then the alternating series test is an obvious possibility. Number 6. Series that involve factorials or other products, including a constant raised to the nth power, are often conveniently tested using the ratio test. Bear in mind that the absolute value of a sub n plus 1 over a sub n as approaches 1 as n approaches infinity for all p series and therefore all rational or algebraic functions of n. Thus, the ratio test should not be used for such series. Number 7. If a sub n is of the form open b sub n closed to the power n, then the root test may be useful. Number 8. If a sub n equals f of n, where the integral from 1 to infinity of f of x dx is easily evaluated, then the integral test is effective, assuming the hypotheses of this test are satisfied. In the following examples, we don't work out all the detail, but simply indicate which tests should be used.